From the screen, the next speaker is Edson de Faria, University of São Paulo. And today Edson is taking us on a guided tour of hyperbolicity for the renormalization operator for CR unimodal maps.
Thank you. Well, it's a great pleasure to be here to be speaking at this conference in honor of Professor Maurício Peixoto, who's one of the fathers of Brazilian mathematics, and in particular a founder of this place of IMPA. So I hope it will be an okay talk. So I will talk about some old result. It's already 5 years old, basically because I don't have anything new in dynamics to talk about. I was working on other things for the past couple of years. And it's joint work with Welington de Melo and Alberto Pinto. And it concerns unimodal maps of the interval, which is here in this talk, normalized to be the interval -1, 1. The critical point is always at 0. So there's some short history of this subject. It starts with some empirical and numerical observations by Coulet and Tresser, and independently by Feigenbaum, who observed that whenever you have like a one-parameter family of unimodal maps, if you record the places along this family where the period doubling bifurcations occur, you take down the values of the parameters and you take the differences of successive parameters for which the period doublings occur, and you take the ratios of these differences. These ratios converge to some universal constant. And moreover, particularly in this paper here by Coulet and Tresser, you see also something about the geometry of the limiting map at the end of this cascade of period doubling bifurcations. They observe that the critical point deploys itself along a Cantor set, and this Cantor set has like universal asymptotic geometry, independent of the family that you pick. Okay? So the proposed explanation for this amazing observations was that there is a period doubling operator, renormalization operator, that has a hyperbolic fixed point, and conjecturally the properties of the derivative of the operator at this fixed point, the spectrum of this derivative, would tell you why these numbers are universal. Okay? So shortly afterwards, Lanford, 1982, he gave a computer-assisted proof of these conjectures, working in a very cleverly defined Banach space of real analytic maps of this type. It's a sort of a very small space in some sense. Everybody there is real analytic. I mean, it's funny. It's a Banach space of real analytic maps. So obviously the norm in this Banach space has nothing to do with, it has something to do with coefficients of power series, but it doesn't really, have anything to do with the topology of real analytic maps. So this was a computer-assisted proof, and more or less at the same time, shortly before actually, Campanino and Epstein gave a proof of the existence of the fixed point for this period doubling operator without essential help from computers. I say it's without essential help because there's some moment in the paper where they use some inequality that they only know it's true because they did some computations, okay, on the computer. But it's quite different from the sort of very difficult interval arithmetic kind of numerical analysis that Lanford had to use in his work, okay? Now, let's see. So the first major tour de force in this area after Lanford's work was done by Davy, this analyst from England. He used some very complicated methods from nonlinear functional analysis to extend Lanford's results, namely the hyperbolicity of this fixed point in this tiny Banach space that he had, to a much larger space of maps, C2 plus epsilon maps. And here epsilon can be any positive number. And I'll come back to that later, but the fact that he gets this hyperbolicity in C2 plus epsilon for every epsilon has to do with the fact that he knows that the fixed point of the period doubling operator is a convex function. Okay, so after that, or actually in the meantime, Lanford and others, and when I say others, I mean David Rand and Ostland and a lot of other people, they realized that the period doubling operator was just the restriction of a much more general operator called the renormalization operator. And they formulated, which involves, the period doubling, as the name says, involves like period doubling, but you can also consider other situations like period tripling or various other kinds of combinatorics. So they formulated a general conjecture, which is this one. It's stated here just for bounded type. I'll explain what that means later. So it says that there is this operator called the renormalization operator, and this operator in this space of unimodal maps of bounded combinatorial type, I'll explain what that means in a while, behaves just like a horseshoe, an infinite dimensional horseshoe. It's a hyperbolic, the limit set is a hyperbolic Cantor set where the operator acts as a full shift on finitely many symbols. You can drop this bounded combinatorial type and, instead of looking at a full shift in a finite number of symbols, you could consider a full shift in uncountably many symbols, say. That's also, a more generalized conjecture, which was later, in fact, proved by Lubitsch in a restricted sense, in a kind of very interesting space that I will talk about in a while. Okay, so the challenge is to find a purely conceptual proof of this conjecture. This was the challenge. And for obvious reasons. I mean, you can no longer expect to do the sort of numerical thing that Lanford had done for, the fixed point, because now you have like uncountably many points to worry about. You have a whole attractor, and, life is too short. So what are the major conceptual breakthroughs in this area? So the first breakthrough was achieved by Sullivan. He tied this theory of renormalization of unimodal maps to the theory of quadratic-like maps developed by Duadie and Hubbard. And he used this theory to prove that at least you had convergence towards this attractor. So he established real and complex a priori bounds, which are actually fundamental in everything we do in this theory. And he gave the first conceptual proof of existence of this attractor. But he was not able to show that there was exponential convergence. In other words, if you take two maps, two unimodal maps with the same sort of combinatorial behavior, the same type of critical point, the same sufficient degree of smoothness and so on, as you renormalize them, they converge together. This is what Sullivan proved, but he was not able to prove that there was a rate of convergence. An exponential rate of convergence was achieved by Mcmullin a few years later, okay? By completely, related but completely different methods in a way, because it uses the theory of rigidity, of towers, and it's in the spirit of the proof of Mostel's rigidity theorem. So it's a very beautiful theory, in its own right, but I'll say nothing about it except that, it's being done. And it's used in our results here. So the final sort of major breakthrough was achieved by Lubitsch. He was able to actually prove Lanford's conjecture, but in a very funny space, a space of quadratic-like germs So these are germs of maps like the ones that I drew on the board here. These are quadratic-like maps. These are complex analytic maps defined on some disk, mapping it onto a larger disk. So in this picture you have U, you have V, you have F. F is a 2-to-1 map that has a degree, it has degree 2, has a critical point there at 0, and it restricts to one of these unimodal maps when you look at things on the line, okay? So he worked on a space of such maps, on germs of such maps, germs around their Julia sets. The Julia sets are just the sets of points, the filled-in Julia set is just a set of points which never escape under iteration by F, okay? I'll explain these things a little bit later. This is just like history for now, so, okay. So he was able to show that in this space, and it's really a funny space. It's a manifold. It's a complex manifold, but it's modeled on a topological vector space, which is not Banach. Okay. In this context, he was able to show that the renormalization operator is analytic. Okay. And and then and he showed also that it's hyperbolic, so it has this hyperbolic horseshoe in it. Okay, what we do, Welington, Alberto, and I, what we do is we prove Langford's conjecture in this sort of much larger space of CR unimodal maps. R here is any real number sufficiently big. It has to be greater than or equal to 2 plus alpha, where alpha is sort of close to 1, is in fact the largest of the house of dimensions of the post-critical sets of the maps in this Sullivan attractor. Okay? And the proof of Lubitsch, the proof that we do uses Lubitsch theorem and also this Davy tour de force of functional analysis. We also go a little bit beyond the conjecture. We prove that the local stable manifolds of maps in the attractor form a C0 lamination, which has a sort of a nice holonomy, smooth holonomy, C1 plus beta for some beta greater than 0. And in particular, if you take any smooth curve of unimodal maps that cuts this lamination transversely, it intersects it at a set of constant house of dimension less than 1, which really means that these maps, these are infinitely renormalizable maps, they form a very small set in this family. Okay? Okay, now there's some recent major results that are, after this work we did. And I'm not going to talk anything about that, except that I have to mention because they're really great results. So there's the work of Avila and Lubitsch, just from last year, where they managed to prove exponential contraction of this renormalization operator along hybrid classes of infinitely renormalizable unimodal maps with arbitrary combinatorics. You don't have to assume bounded type. And moreover, you don't even have to assume that the maps have quadratic critical point as we do. Any criticality will do. And from that, they deduced that the orbits of this renormalization operator are asymptotic to a full horseshoe now that includes not just bounded type, but all sorts of combinatorial types. And as I said, their methods apply to polynomial-like maps with one critical point, and they yield like a unified approach to this sort of hyperbolicity problem. But always, I insist, this is always in this space of, germs up to some form of affine equivalence. Okay, so, here. So the theorem that we have as, if you put everything together, the structure of what we have to do to get the hyperbolicity conjecture of, the Langford hyperbolicity conjecture, is given in a diagram like this one. So at the top, you see the real and complex bounds of Sullivan. They come into play in everything. These arrows, I should warn you, when you see a box and you see an arrow joining this box to another box, this doesn't mean that this implies that per se. It just means that what you see here in the source is a crucial ingredient in proving the target. Okay? And in fact, if I was going to be really honest, there should be an arrow going from here to almost everywhere here, okay? Directly. But in any case, because the bounds are used over and over again. So the real bounds were used by Sullivan to produce the existence of the topological attractor of the renormalization operator. This is called K. And actually there are various Ks depending on which combinatorics you fix. And this theorem is important in Mcmullin's result, which shows the exponential contraction. Of course, it's important because he's showing something about this horseshoe here, right? So, it's about this limit set. The real bounds are also used by Lubitsch in his combinatorial rigidity theorem, which is used to prove something called the no small orbits theorem, which takes care of the expanding direction of the renormalization operator. And putting these things together, that's just a part of it, but Lubitsch was able to prove this sort of major breakthrough. He was able to show that the renormalization operator is hyperbolic in the space of quadratic-like germs. So this is a space of germs of quadratic-like maps like the ones drew on the board. And it turns out that stable manifolds, for example, correspond to what we call hybrid classes. So In the board, I drew two such quadratic-like maps and a conjugacy between them. I say that they are hybridly equivalent if this conjugacy is a quasi-conformal map with the property that its distortion at the Julia set vanishes almost everywhere. Okay? So it turns out that the hybrid classes are the stable manifolds in this Lubitsch space. Okay, now, the problem is that this Lubitsch space is an abstract space modeled on this complicated topological vector space, which arises, in fact, as a direct limit of Banach spaces. So it's, you know, it's not very pleasant, and in fact, it's not large enough for what we want. We want something. In the end, we want to state a hyperbolicity result for CR. Okay. So first, what we do is we take Lubitsch's result, which is in this abstract manifold space, and we push it down to a Banach space, just like Lanford space, except that now it's something that contains the whole attractor of the renormalization operator, not just the fixed point like the Lanford, the period doubling fixed point. And once we have that, we can combine this with some very interesting techniques by Davy, coming from functional analysis. There's a linear part, and there's also a nonlinear part. The linear part of Davy's techniques allow us to define what the tangent spaces to the stable sets in CR are, what are the natural candidates for that. And the nonlinear techniques allow us to prove an abstract stable manifold theorem for certain operators that we call robust. I will define these things in a little while. And combining everything, we get the full hyperbolicity conjecture, okay, for bounded type. Now, let me try to be a little bit more precise. So the unimodal maps that I'm considering are always defined on the interval -1, 1, critical point at 0. The critical value is always at 1, which is the rightmost point. And we have to consider various Banach spaces. So one Banach space is the space of even CR functions, which vanish at the origin with the CR norm. So most of our unimodal maps will be embedded in this space. We also have to consider a more restricted space, a space of maps which are not just even, they're actually factored through the map x goes to x squared. Okay, and again, you take the CR norm, but you take the CR norm, you take the CR norm of phi here, okay, which is the thing which is composed with x squared. Now, the spaces of unimodal maps that we consider sit inside these spaces, essentially. They actually sit inside affine spaces, which are just translations of AR and BR, okay? So we just have to think of UR as the space of CR unimodal maps like the ones that I drew there, which are even, okay? And they also have to have, the second derivative has to be strictly less than 0 at the critical point. So this in fact requires, I'm having trouble with this. So this in fact requires R to be at least 2, okay? And VR is something similar. It's the space of unimodal maps which are compositions of certain diffeomorphisms with x goes to x squared. The situation is such that the BRs and the B's and the A's, they are related in this fashion, okay? Each BR is contained in an AS provided S is less than or equal to R. Okay, so what does it mean to renormalize a unimodal map? So a map is renormalizable if you can find a number P, which is the period of the renormalization, such that if you look at the interval formed by Fp of 0 and minus Fp of 0, and you look at Fp restricted to that, that map is again unimodal and it maps this interval into itself. Okay? If this happens, you say the map is renormalizable with period P. Provided P is the smallest possible with this property. Okay, so here's the definition of the renormalization operator. Okay, I'll draw a picture. So you have these intervals. You can consider these intervals. The interval containing the critical point, which is interval minus lambda up there. And, this interval here, and its images under F. So these are pairwise disjoint intervals deployed inside -1, 1, and they are deployed according to a certain order. So there's a permutation called the unimodal permutation, which describes this relative order. So the set of all unimodal permutations I denote by P, by bold P. So here's a picture. So here's the interval -1, 1, and you were supposed to imagine that there's a map from this interval into itself, which is unimodal, which is F. And you see the critical point there in the middle. To say that the map is renormalizable means that there is an interval, symmetric interval containing this critical point and a bunch of other intervals, okay, which are pairwise disjoint with the property that F maps, well, first it maps this red interval into the rightmost interval, which is the one containing the critical value, folding it. And then the remaining ones map diffeomorphically. Okay? So these intervals are shuffled around. What is to renormalize? What is the meaning of renormalization? It means just take the first return map to this red interval, then you linearly blow it up to unit size again and consider the rescaled map. Okay? So that's what renormalization means. All right. Now, here's some notation I'll have to use to state some results. So the set of all unimodal maps of class CR which are renormalizable with a given unimodal permutation. What is a unimodal permutation? It's one of these permutations that you see in this picture, in the previous picture, yeah? So it turns out that they are, if you graph the permutation, you see that it also has a unimodal shape. Okay, this is why they're called unimodal permutations. So if you look at the set of maps which are renormalizable with the same kind of permutation, that forms a connected set, subset of the set of CR maps, and I denote that UR sub theta. So with this notation, the renormalization operator becomes, like so, defined on the union of these UR sub thetas, where you vary the permutations through all possible unimodal permutations. And you can also talk about infinitely renormalizable maps. So you can take a sequence of permutations belonging to, well, now I'm actually fixing, and from now on I will do that, I will fix a finite subset of the unimodal permutations, and I will only consider maps which are renormalizable with permutations in this set. So if I take a sequence, if I take an infinite sequence of such permutations, I can consider the maps which are in this intersection here. These are the maps which are infinitely many times renormalizable, and every time you renormalize a map which had a permutation theta sub n, you get something which is renormalizable with a permutation theta n sub n plus 1, and so on. Okay? So you can consider the union of all such things over all sequences of permutations in this set, and what you get is what we call the infinitely renormalizable maps with combinatorics belonging to this set theta. So since the theta is supposed to be finite, we call them bounded combinatorics. Okay, so these are maps of bounded combinatorics belonging to theta. I will also need some complex spaces here to state the theorem. So first you consider the real Banach space of holomorphic functions on a V, such as the one I drew there in the board. These V's are always symmetric about the real axis, and they always contain the interval -1, 1, which is the interval that interests us. So inside this big Banach space, I'm thinking only of maps which are continuous up to the boundary, and I take the C0 norm, so this is an honest Banach space. I consider a closed subspace of that, which is the space of, it's a closed linear subspace of functions which factor through z goes to z squared, okay? Through a holomorphic map. Now, inside the space, I define a space called U sub v, which is the set of all functions. It's not exactly inside the space. It's inside a translation of this space, an affine subspace of H0 sub v. So it's just 1 plus A sub v. In there, you have this U sub v, which is a set of all functions which are of the form 1 plus phi, where phi is in AV, okay? And in fact, you want more than that. You want so these phi's, they factor through z goes to z squared. You want this thing here, this guy who comes here in front, to be a univalent map on some neighborhood of -1, 1, and in such a way that the restriction of F to -1, 1 is a unimodal map. Okay? So So this is an observation that essentially I made already. U sub v is contained in this affine subspace of this Banach space. And I will always identify this affine space with the Banach space itself. I hope nobody is offended by that. So U sub v is in fact open here, and therefore it's a Banach manifold, okay, in a natural way. I will not care about all kinds of v's. I will care only about certain types of v's. I will only care about the v's which have this form. They are neighborhoods of the interval minus 1, 1. There's a set of points in the complex plane whose distance to the interval minus 1, 1 is smaller than a, where a is a given positive number. Okay, now, with this notation I can state the Sullivan complex bound. So the idea is that after enough renormalizations, every map which is infinitely many times renormalizable and belongs to this U sub v with the special v that I just defined becomes quadratic-like with a definite modulus. The modulus is just the modulus of this annulus that you see there, v minus u in the picture here on the board. So Sullivan's theorem is as follows. You take any finite set of unimodal permutations, then the theorem claims, the theorem states that there exists an A, a compact subset. Here there is some sort of abuse of notation, but anyway, remember this guy is actually, I'm identifying this guy with the affine copy of it, which is a translation by one. So you look at unimodal maps which have this complex analytic extension to this neighborhood of the interval minus 1, 1, and you only care about those which are infinitely renormalizable and real analytic, as I put there. Okay. So there exists a compact subset of this space and a positive number mu with the following properties. So every map in this compact set has a quadratic-like extension whose conformal modulus, the conformal modulus is just the modulus of this difference v minus u, is bounded from below by this constant mu. Okay. Second thing is that the renormalization operator leaves this compact set invariant. Okay? And the restriction of R to K is in fact a homeomorphism which is topologically conjugate to a two-sided full shift on these theta symbols here. Oops, my God. Okay? And moreover, if you look at any G which is infinitely renormalizable, but of class CR now, okay, and which is in VR. What's VR? Remember, VR were the unimodal maps that factor through x goes to x squared. Okay, so provided R is greater than or equal to 2, the orbit of G under renormalization will be shadowed by someone in the attractor, in this K, in this compact set K. Okay? And in fact, the distance will converge to 0 in this zero topology. This on the interval, the distance goes to 0 as n goes to infinity. But as I said, Sullivan was not able to provide any rate of convergence here. The rate of convergence, also this is just a remark of what item 2 of the theorem says. It says that R restricted to K is topologically conjugate. My God, I can't believe this. It's conjugate to this shift map here. I can't believe there's somebody calling me here. So anyway. Okay, Mcmullin was really the first guy to establish convergence at an exponential rate towards this K. Okay? Now, so here's Mcmullin's theorem. So Mcmullin proved that if you take two infinitely renormalizable quadratic-like maps, okay, with the same bounded type combinatorial, bounded combinatorial type, and with conformal moduli, oh my God, with conformal moduli, I'm sorry about this, I'm not used to this thing, so with conformal moduli greater than or equal to a constant mu, then their renormalizations converge together in the C0 norm exponentially fast, where the constant, the exponential rate depends only on this combinatorial types that you're fixing, but do not depend on this conformal moduli. The constant that you put here in front may depend on this conformal modulus. Okay? All right. So this is Mcmullin Theorem, and it was important in the Lubitsch Theorem. So what is Lubitsch Theorem? Lubitsch, I'm going to be very vague here. So Lubitsch endowed the space of quadratic-like germs with a nice complex manifold structure, as I said before, modeled in a topological vector space. This vector space arises as this topological vector space arises as the direct limit of certain real Banach spaces of analytic functions. Okay, and the attractor is embedded there. So the theorem by Lubitsch, stated in a very vague way, is this: in the space of quadratic-like germs, this renormalization operator is complex analytic, and its limit set K inside that space is a hyperbolic basic set. Okay? And this is really a deep theorem. So now, this deep theorem is the starting point of our story for us. Okay? We take this and we do something with it. First of all, we have to transport it, this hyperbolicity statement, this hyperbolic basic set structure, we have to transport it from this crazy Lubitsch space to a more manageable space, which is a Banach space. So this first theorem we prove is that we have such a situation. We have an open set in a Banach space, which is this Banach space I had defined before for this neighborhood omega sub A. So there exists an A. Okay, so there exists a neighborhood of omega sub A, an open subset of this Banach space A omega sub A, containing the attractor, okay, and a positive integer n, which is just the power of the renormalization operator, with the following property. You find a real analytic operator, T from O to A, which has this K has a hyperbolic basic set and is precisely, T is precisely the, it's essentially the nth power of the renormalization operator when you restrict it to the interval -1, 1. Okay? So this is what we prove first. And the ingredients are, of course, Lubitsch theorem. We use the complex bounds given by Sullivan again, and we also use a notion of a skew product. There's a skew product renormalization. I'm not going to go into that because it's, I don't have much time. So, well, now you want to prove hyperbolicity in CR, but the problem, the basic problem that appears here is that, well, the renormalization operator is not a Fréchet differentiable operator. It involves compositions. So as soon as you have compositions, a composition operator is not better than continuous when you look at it as a map from CR cross CR into CR, right? So you face this difficulty that the operator is not Fréchet differentiable, okay? So you have to go around that somehow. So, what does it mean to say that the operator is hyperbolic? That's a question, right? Well, you can still talk about the hyperbolic picture. So, you can still talk about having some, you define the stable sets, the unstable sets, and you say, well, maybe these are manifolds and they're kind of transverse to each other. And, along the stable sets, you have some sort of exponential contraction. Along the unstable sets, you have exponential expansion. And so, to make this notion more precise, I say that suppose you have a continuous operator on some Banach space, on some open set in a Banach space, and you have a compact invariant set, then the hyperbolic picture is what you would expect. You say that the hyperbolic picture holds true for T if there exists a constant between 0 and 1, which is basically going to govern the contraction and the expansion that you can have with the usual properties. So the local stable sets and the local unstable sets are Banach submanifolds of this Banach space. You have contraction along the stable. Well, here I think I forgot an epsilon, but anyway, never mind. So you have contraction along the stable sets, and you have also expansion along the unstable sets. Okay? There's this condition here that you have to require the T to be invertible along the unstable directions.
So how smooth can we effect on this? Are the Banach submanifolds themselves smooth submanifolds?
Yes, when I say Banach submanifolds, I really mean like at least C1 submanifolds. But you see, the operator for this picture, in the definition, the operator is merely continuous. You see, in the definition of the hyperbolic picture, we don't use the derivative of t at all. Okay? We don't use that it has a derivative.
But your maps were in CR, right? And you lose derivatives in the submanifolds or not? Or your maps
I'm not claiming that the submanifolds are any better than C1. Okay, and in any case, this is a definition, right? The definition of a hyperbolic picture. So I say that the hyperbolic picture holds for an operator T like that. If these conditions are satisfied, there's more conditions here. So you also need to know what you would expect. I mean, if you have the unstable manifold here and you're taking a point which is not in the unstable manifold, as you iterate, as long as you don't escape the domain of definition, you would expect to have this exponential approach towards the unstable manifold. Okay? So that's this third condition. And you also want something to hold true about the local stable manifolds. You would like them to form a C0 lamination. If all of these things happen, then you say that the hyperbolic picture holds for the operator. And the theorem that we prove is that this hyperbolic picture holds for our space of, for our renormalization operator in the space of CR unimodal maps which are even. As long as this R is greater than or equal to 2 plus alpha, where alpha is a number very close to 1. It has to be larger than the largest of the Hausdorff dimensions of the maps and the attractor. Okay? Furthermore, we prove that the local unstable manifolds are real analytic curves. So I think this actually answers some of your questions. So in this case, the manifolds are really very nice. The unstable manifolds are one-dimensional though. So that's not. And the local stable manifolds are of class C1. We are not able to prove that they are better than that. Okay? And probably they are not. But they have a nice holonomy. They have the stable manifolds form a continuous lamination whose holonomy is C1 plus beta for some positive beta. And I'm being a little bit, this is my silly attempt at being funny here, okay? The proof is long, but not painful. I should have written, the proof is long, but not too painful. It's kind of painful, okay? This is by contrast with something you'll see next. Well, so there's some key steps in the proof of this theorem. You have to start with the power of the renormalization operator. And you have to first extend the hyperbolic splittings that you have in the space, okay? Just at the level of the derivative. So this linear part depends on a notion that we call compatibility of spaces. If I have time, I don't know how much. I have 10 minutes, so I don't know if I have the time to put these definitions. But there is some notion of compatibility. I'll tell you in a minute. That comes into play here. So first you find that, you have the hyperbolic splitting in your space of, like in the Banach space that we got from Lubitsch space, and you want to extend it to a larger space. So first you extend the splitting, okay? So you have nice candidates for the stable manifold, for the tangent space to the stable manifolds now. The second thing is you want to show that the stable sets in the larger space are actually graphs of C1 functions over these stable subspaces that you extended. So this nonlinear part is something that depends on the notion of robustness that I will state in a moment. And with this notion in place, we can actually prove a general stable manifold theorem for robust operators. So let me see if I can tell you quickly what these things are. So compatibility is a notion that involves three Banach spaces. So you're supposed to think that there's an operator defined on A, and there's two larger spaces, B and C. These inclusions are merely set theoretic inclusions. I do not mean to say that this is a subspace of that or anything like that, okay? So A is like the analytic things, B is like the CR things, and C could be, for instance, just the continuous things, okay? So each one of these inclusions is, in fact, if you look at it carefully, it's a continuous inclusion, okay? Bounded linear operator, right? As inclusion. But it has, in general, a dense image, which complicates matters tremendously, actually. So compatibility means you have an operator on A, you have these spaces B and C. So there is a C1 operator defined on A, and it has a hyperbolic basic set. You already know that. So you want to extend the derivative at each point of this hyperbolic basic set. You want to extend the derivative and its hyperbolic splitting from A to B. Okay? From A to B. So you say, what the hell is C doing here? C is here to ensure some form of compactness. So it's always a kind of Ascoli principle. If you have boundedness in this larger space, you have precompactness in the smaller space. Okay? Now, if you want to be technical, here's the definition of compatibility. I hope not to bore you to death with this definition, but you know, I say that a pair of spaces BC, like here, is rho compatible with the operator T with respect to this hyperbolic basic set, where rho is some constant between the contraction constant for the hyperbolic basic set and the minimum amount of expansion that you see there. Okay? So take any constant between those two numbers. You say that this pair BC is rho compatible with TK if the following things happen. First thing that should happen is that the inclusions that I told you about should be compact operators, not just bounded, but compact. They should map bounded sets into relatively compact sets. And it's sort of amazing, actually, if you come to think about it, that such compact operators can have dense images, right? Now, you have the following condition. These operators should have the following. So now, I'm sorry. So now you look at the derivative of the operator T in the A space at each point X of the hyperbolic basic set. For simplicity, I'm calling these linear maps, these linear operators, L sub X. Okay? So each one of these maps should extend as a bounded linear operator from C to C. C is the largest of the three spaces. And in fact, they should be extendable in a uniformly bounded fashion, like here. Okay? Each one of these extensions should leave B invariant. And if you look at the operator in B, it is also a bounded operator. I don't know why I wrote it like that, but you know, I think I meant for every V in B. Okay? All right. So you also want these linear operators, L tilde. Yeah, L tilde is the restriction of L hat to B, right? You want these guys to vary continuously with X. Okay? And then there's a technical condition that has to do with approximations that would take me a long time to explain. It says that, you know, maps in the unit, elements of the unit ball of B can be approximated in the C norm by elements of A, okay, which have bounded B norm, bounded by some constant that in general is greater than 1. This is kind of a technical condition, but it's very much necessary for the proof. And this is even more technical. Maybe I won't go into that, but this is just saying something about the growth of the iterates. I mean, these linear operators, they are, as you iterate the operator, T, by the chain rule, you have to compose L of X with L of T of X and with L of T2 of X and so on. So these compositions are indicated like that. Okay, so this is like the mth iterate of the derivative. And this thing has something to do with the growth of these norms, of the B norms of these derivatives. And here I should really have, I think I made a mistake here. I think this should be an L tilde, not an L hat. But in any case, they're the same. Okay, so the theorem is that if you have compatibility, if you have two Banach spaces and this pair of spaces is rho compatible with this TK, then the splitting extends. You can extend the splitting. So you have a splitting of stable and unstable spaces, and the splitting continues. But you cannot really, you just have some sort of separation in the spectrum. You cannot really claim that it's, if you had a hyperbolic splitting in the original space, that you now have a hyperbolic splitting again. This will only happen if this rho, you can only guarantee that if this rho is less than or equal to 1. Okay? So the theorem is that for the actual renormalization operators, so if you have T and K as above, meaning T is a power of the renormalization operator and K is actually the attractor of the renormalization. Now, the Sullivan attractor. Okay? And if you look at the expansion that you have in K, call it lambda, then for each alpha greater than 0, this pair of spaces is 1 compatible with tk. So what is A2 plus alpha? A2 plus alpha is the unimodal space that I defined earlier, corresponding to C2 plus alpha mappings. And A0 is just like continuous unimodal maps. Okay? So this pair of spaces is 1 compatible with tk. So in particular, the splitting extends as a hyperbolic splitting in this space here. The second step, which is needed for robustness, also says something about the compatibility of this pair of spaces where you have slightly less than 2 derivatives here with tk. Okay? Why this is needed is only going to be clear if I define what robust means. So what is robustness? What does it mean for an operator to be robust? An operator is robust if it satisfies, roughly, this is a very informal definition, if it satisfies these conditions here. So it should act on 4 Banach spaces now. Now for some technical reasons, we cannot do with just 3 spaces, we need 4 spaces. So now you're supposed to think that A are the analytic maps, B are the CR maps, C is like the CS maps where S is greater than R plus 1. You have at least a gap of 1 derivative from one to the other to ensure compactness. And D is like just the continuous things. Okay? In A, you have a hyperbolic basic set with expansion constant lambda. The pair of spaces BD is 1 compatible with TK. The pair of spaces CD is rho compatible with TK for some rho less than lambda, where lambda is the expansion constant. Okay? But rho could still be larger than 1. So you can't really guarantee that the splitting that you get in C is hyperbolic. But only that there is a splitting with a gap, okay, in the spectrum. So as a map from B to C, T should be C1. And this is what happens with the renormalization operator. If you look at it, if you look at the expression of the renormalization operator, which I will give you in a moment, it should, it should be clear looking at the expression that this map is C1. Okay? It also satisfies some other technical conditions. It has to be Gateau like a Gateau differentiability condition for the operator in C when you look at directions in B. Okay? And the extension of the derivative, extension of the derivative dt to B should be a reasonably good approximation of T. It would take me too long to explain what reasonably good approximation means, but it can be done in a very precise way. And so here's the theorem. So the theorem is that, first, an abstract stable manifold theorem. If you have a robust operator in the sense that I just described, defined on the space A, okay, which is hyperbolic over this K, this hyperbolic basic set, and robust with respect to 3 other Banach spaces, then the hyperbolic picture holds for T acting on B. Okay? And then you deduce what you want also, that the local unstable manifolds are CK with K greater than or equal to 2. In fact, reanalytic curves. And the local stable manifolds are of class C1 and they form a C0 lamination. Nothing here is said about the holonomy. And now, this is my further attempt at being funny. The proof is long and painful. And I also say it has uncountably many norm estimates, so someone may protest, but there are only really finitely many estimates. But since the title is hyperbolic something, I'm allowed to be hyperbolic, right? So this is uncountably many estimates. Finally, you prove that the renormalization operator is robust. So everything I said carries through to the renormalization operator. So instead of dwelling into these statements and so on, let me try to give you an idea. I overstepped my time. So if you give me just 1 minute, I can try to convey why, where are the estimates coming from? So when you look at the formal expression for the derivative of the renormalization operator, you get this horrible formula here. F is your unimodal map where you're derivating the, calculating the derivative of the renormalization operator, and V is like a vector field, a perturbation of F. Okay? So here's the formal expression. Now it turns out that to do this theory and prove robustness, compatibility, and so on, what you have to control are these derivatives that you see here. See? D, F, J, so J is some power of F, at some point there in the middle, at one of those renormalization intervals. You have to do that, and it turns out that using the mean value theorem and some distortion estimates, these derivatives are actually controlled by ratios of successive intervals in this when you have a infinitely renormalizable map, you have like a Cantor set, which is the closure of the orbit of the critical point, and it has a hierarchical structure of intervals. And what you see here are ratios of intervals from the same generations. Okay, they're in the same generation. So these ratios control these derivatives. So what you need is the key geometric estimate involves proving this theorem here. So, and this is why you have these 2 plus alpha and 2 minus alpha and so on. Okay? So you need to show these two estimates. D here is the supremum over the Hausdorff dimensions of the closures of the post-critical sets of the maps in the attractor. And this estimate says that these things are decreasing exponentially as you go from generation to generation. And this says also something similar to that. Since I'm out of time, I guess I'll stop here. But,